As you can see from the heading of circular fillet weld in torsion, we are going to discuss the case when we have a circular fillet weld subjected to torsion. But this is not something that we do not know about. We have discussed this earlier in detail. But the concepts that I am going to tell you in this particular video are such concepts which are generally not covered and not explained in any other source, and this is something where you can get confused in your exams. And not only this, but if you watch the video till the end, you will be able to take out some of the concepts, some of the learnings, some of the conclusions that will be useful for you as a general for other questions as well. Okay, so let's start discussing about this concept. Keep this thing in mind that since we have already discussed this, so I will not be in detail explaining this whole process and this whole weld and how the stress is generated in this case. Rather, I will be coming fastly to that point which I want to convey to you. Okay, so this is the case when we have a shaft which is fixed to a rigid support here, and both of them are joined with a circular fillet weld. Okay, we apply a torque, external torque on the shaft like this. Due to the torque, this shaft will have a tendency to rotate, to move, to twist. And this bottom part of the weld, which is joined with the shaft, that will also try to move with the shaft, because obviously both of them are joined together. So if the shaft moves, this lower part of the weld will also move. But this side part of the weld, this part, which is linked with the rigid support, that is not going anywhere, because rigid support, this support is fixed. It is not moving as a result of torque. So this part of the weld will also stay there. So if you look at the cross section of this weld, one part of this weld is trying to move with the shaft, which is subjected to torque, which is subjected to torsion, but one part of it is fixed. So as a result of it, there will be shear stress, right? And as we have discussed, as I have explained to you in the earlier videos, that shear stress is that we consider that along throat section of this weld. Now, what is throat? Why do we consider the critical section to be throat? All these things we have discussed earlier, so I am not going to explain that here. But the thing that you should keep in mind in this case is that this part of the weld which is subjected to the shear stress is having a shape something like this, right? You can see that this is somewhat tilted. It is in the shape of a tilted ring because throat is tilted. So the circle that you will get from that tilted throat will be something like this. Okay, now come to determine the value of shear stress in this case, the shear stress generated inside the weld. So that is going to be decided by the torsion equation, Now, there is a common confusion among students, among beginners especially, that torsion equation you can only apply for shafts. So it's not like that. You have to apply them for shafts because obviously shafts are axisymmetrical, but actually you can apply the torsion equation for any such component or body which is axisymmetrical, which is symmetrical about the axis. Okay, it has a regular shape and it can be a solid or a hollow shape. Okay, so in this case, if I try to apply the torsion equation, tau is equal to TR by J for this section, okay, which is going to get sheared, along which the shear is going to happen, there are going to be certain issues. The issues is that this particular section is not confined to a single plane. That is an assumption, that is a limitation of this torsion equation. And this is not confined to a single plane, rather it is tilted, right? So what I am going to do is that I will assume this particular thing to be in a single plane like this. Okay, I will assume that instead of it being tilted, it is in a single plane. And how I can do that? I can do that because the difference between, let me draw a bigger view of this. if we have the weld like this is the throat, and if I assume this length to be same as this length, if I consider OA to be almost same as OB, then there is not much of approximation because both of them are nearly same. There is very small difference between these two lengths, and by doing this assumption I will be able to use the torsion equation and do the analysis very easily, because such analysis can be done for those type of bodies which are confined to a single plane, right? So that is why this is the first assumption that we are doing. In this whole video, I am going to tell you about 2-3 assumptions and what is the impact of those assumptions. And that is what which is generally not discussed in different sources. Okay. So this is the first assumption that we are making, that instead of this being tilted, we are taking it as straight. But this is an assumption that you have to take, otherwise you cannot proceed. And it's a very small assumption as far as accuracy is concerned. So we will assume that this tilted part is actually in the shape of a ring like this. The outer part of this, you can call it to be RO. Okay. The inner radius is RI, and there is going to be a value of radius which is going to be between them, and let's call that value to be R average. Now if we try to put these values into the expression of shear stress, where actually we want to calculate the maximum shear stress generated, you will put the value of T as obviously T only. The value of R will be the maximum value of R, the outermost value of R. That's how we solve it, and that is equal to RO. Correct? This is RO. In this diagram, this is RO. This whole length. This is RI. Okay. And how do you calculate the exact value of J? You know that for shapes like this, when we have, you can say, a ring or we have a thin hollow disc. So in that case, the value of the exact value of J is determined by pi by 2 RO to the power 4 minus RI to the power 4. Correct? So you put this value here, pi by 2 RO to the power 4 minus RI to the power 4. This is the expression for the exact value of maximum shear stress. There is a little bit more information that you can learn from here, that RO actually is equal to RI plus T. Correct? RI plus T, where T is the thickness of throat section. Always remember that this diagram has been concluded from this, and this is coming from this, where this is T, and we assume this length also to be equal to T, as I explained here. Okay, so this is T is the throat thickness. So RO is equal to RI plus T, and you can also learn from here that R average is actually lying midway of RI and RO, and it's important for you to clear the concept of average R here, because this is something which confuses many aspirants, and there has been question in other parts of the syllabus where inner radius, outer radius and average radius has created confusion among aspirants. So it is important for you to listen to this carefully, that average value of R here is lying between RI and RO. So it is at a distance of T by 2. You add T by 2 to RI and you will reach R average, or you decrease T by 2 from RO and you will reach R average. So this is how you can define R average. Okay. So in this case, RO is actually equal to RI plus T. Similarly, here also you can relate RO and RI like that. So this is the exact expression to find out the shear stress. But you will not find this expression in any of the sources, or whenever you are solving question, you will not find that any source ever uses this expression. However, this is the most exact expression. If you forget this small approximation, then this is the most exact most exact expression to determine the value of maximum shear stress. But why is it not used, and what is the learning behind that? That is what I wanted to share with you. Okay, so now let's try to change the exact value of J to a little bit easier and approximate value. Okay, so the value of J that we have here is pi by 2 RO to the power 4 minus RI to the power 4. Now, as I told you, RO can be written as T by 2 added to R average, right? This is RO, this is RI, and average is lying between this at half distance of T. So if this is R average, you need to add T by 2 to R average to reach RO, right? And you need to subtract T by 2 from R average to reach RI. That's what we are going to do here. If you write this as R average plus T by 2 to the power 4 minus, you can write Ri as R average minus T by 2 to the power 4. And now you try to simplify it. How you can do that? You can write to the power 4 as square whole squared. Square whole squared. Now you apply a square minus b square, correct? So that will give you, let's write R average only as R, okay? R average is almost equal to R. So what you can write is, this is A square minus this is B square, okay? So you can write it A plus B and A minus B, okay? Let's keep it like this only. And here what we can do, we can again use a square minus b square here. So that will give us a plus b. So t by 2 will cancel and will be 2r multiplied by a minus of b. So r and r will cancel, t by 2 will be added, it will become t. Okay. So this is pi by 2 multiplied by this whole expression multiplied by 2tr. Okay, now let me clean up a little bit. Now if you simplify this expression, I mean this particular expression, so it will give a square plus b square plus 2ab plus a square plus b square minus 2ab. So plus 2ab minus 2ab will cancel and this is the expression that you will get. You can calculate that on your own. And if you simplify it further, so this 2 and 2 will get cancelled, this will be pi rt. So it will be 2 pi rt multiplied by r square plus t square by 4. So this will give you 2 pi tr cube, 2 pi tr cube plus pi r t cube by 2, pi r t cube by 2. Okay. Now in this expression, if we assume that this weld is very thin and t is very less as compared to the radius or t is very less as compared to the diameter, this r is average radius. Okay, again I am reminding that initially instead of r average I used r. Okay, so if I use this expression, then I can neglect this particular expression because it is having cube of t and t is very small as compared to r. So I can write the approx value of j, as 2 pi tr cube. The exact value of j was this, pi by 2 ro to the power 4 minus ri to the power 4. But the approximate value is 2 pi tr cube, where this r is r average. Now what to do? We can use actually this expression in place of r exact to find out the value of maximum shear stress, but there will be one more change that you can do here. The change is that since you have assumed that the weld throat thickness is very less as compared to the radius or diameter of this particular shaft, you can also conclude that from this particular expression you can also conclude that RO is almost equal to R average is almost equal to RI. These are the two conclusions or assumptions which will go hand in hand, because if the value of thickness is very small as compared to the radius, you can say that all the value of radius or all the value of diameter, inner, outer or average, is going to be more or less same. So this conclusion you can draw from this assumption. Okay, so what you can do actually, that in place of R average you can write R in. You can write R in. Now why am I focusing on writing R in? Because R in is something which will be known to you in maximum questions, because R in means this radius here for the weld is nothing but the radius of the outer radius of the shaft, and that will be known to you. That is why it is beneficial for you that we can use directly R in here. And also in the expression of shear stress that we have here, what do we have? We have TRO, that also we can take as RI. TRI divided by the approximate relation 2 pi T RI cube. Generally what you will see in all the books and all the sources is that they will just use R here. And now students are very confused because in this expression R, what they use is the radius of shaft, because Ri is nothing but the radius of shaft, but the value of J is used of the weld. So students get confused that how is this happening? R we are taking for the shaft, J we are taking an approximate value of the weld. So this is also confusion among students. So from this whole discussion, we concluded that the exact value of shear stress is this, where this is RO. How to calculate RO? Ri plus T. What is Ri? Ri is the radius of the shaft. J is, it is the exact value, but you can use an approximate value, an overall approximate relation of shear stress as this, where in place of exact expression of J, you have used an approximate expression, and also the approximate expression is not this or not this, rather it is 2 pi T R average cube. This is the approximate relation for J, but we made R average as R in. We took the value of R average as R in because we neglected the value of T as compared to R. You concluded this expression here by some assumption which told you that the thickness is very small as compared to radius and diameter. So let's remove that particular part. And since you are taking this, so you can also take this. That is why we have replaced R average as R in. Okay. So the assumption from here to here can also be applied to conclude this expression from this. Okay. So this is the approximate expression that you will have for shear stress, where you can directly use the radius of the shaft given to you to find out the shear stress generated in the weld, because R in both the places is nothing but the radius of the shaft. Now in this whole discussion, we concluded that although the exact expression is this one, but all the books, all the sources, whatever source you refer to is going to use this expression even for solving the questions. Now why is it happening? And it is not that the difference between these two is very small. Okay, there are 2-3 assumptions involved. Okay, this is also an assumption. On the basis of this, we also made another assumption. So there are assumptions involved, but still we do not prefer to use this exact expression. Rather, we use an approximate expression, even the difference between them is sometimes significant. So the reason for this is that firstly it's easier. Mathematically it is easier, because suppose you have a question in which radius or let's say thickness of throat T is not known to you. Okay, and R in is given to you, means the average the radius of shaft is given to you. So you will convert this RO in terms of Ri and T. You will write it as Ri plus T. But what about here? Here you will write it as Ri, means radius of shaft, plus T, and it will be to the power of 4. So if you open this expression, you solve this, it will be a expression, it will be expression in the power 4, which will be difficult to solve, right? So just to have a small accuracy, a small increase in accuracy, you have to solve a quite complex equation. So that's why first reason is not preferred, mathematical reason. The conceptual reason why we prefer this expression over exact expression is to have a safer design. You have covered machine design till now, and you have a very good idea that we always try to make the design safer, right? Sometimes we do not go by the exact formula. If we are, there are many cases actually, let's not discuss all the cases here, but we have been discussing all those cases where, we take some of the assumptions to make the design safe, even to consider the failure at throat. The failure is not necessarily going to happen at throat, but we take it to be as at throat due to the same reason. I explained that to you, right? Hence, in this case, you have taken an assumption that the thickness of throat is very less as compared to the radius or diameter, or in general the weld thickness, overall size of the weld is small as compared to the diameter. This is what you have assumed, correct? On the basis of that, you are doing all your design and calculation, but in reality it may not be the case. This expression has been derived by this assumption, otherwise this will give you exact answer. But since you have taken this assumption, you have assumed that the weld is small. In reality it is not small, but you considered the weld to be weaker than it really is. So you did whole designing by considering the weld to be weak, rather assuming it to be strong. So that's a plus point as far as design is concerned, because now you will do all the calculations by considering the strength to be less, because you considered that weld is small, thickness is less, weld is weak, but in reality weld is not weak. So your design is on the safer side. Hence we have sacrificed some accuracy. Obviously we have sacrificed the accuracy when we are choosing this expression over this one, but this accuracy, the loss in accuracy is beneficial to us because it is making the design safer. So this is something which is generally not explained in any of the sources and books. So the point of discussing all these concepts was to convey to you two things mainly. First is that the exact expression for this case is not the expression that you use, that we all use. Rather, this is the exact expression, but we still go with the approximate expression because it is mathematically simpler, and second, it goes with the basic concept, basic principle of machine design, that we choose to make design little bit safer even by sacrificing the accuracy. Okay.